topic 11 today. Before we get into topic 11, I just want to talk about kind of the schedule for the rest of the course. So we have this last topic on air quality. I'm not sure how long it's going to take. I'm estimating a lecture and a half, and I'm hoping to talk about the exam in a bit more detail on Wednesday. But in anticipation that I'm not going to have a ton of time, I'm basically planning an extra review session where we'll do some problems and kind of go over some of the big beats of the course on Thursday. So that's optional on Thursday. I know classes are technically done on Wednesday, so I can't force you to be here on Thursday. But I'll make it worth your while. It'll be about an hour, like I said, going through some different problems and things like that, and kind of talking about the course in general. And that'll be at 10 a.m. And I'll send a link and some more information about that probably on Wednesday. And then we have our final exam. So a little bit of time in there. We are pretty close to the end of the exam period. So I know you're thinking about all of your other courses first, but we'll have to do our exam as well. And if you have, if you want to meet any time in the exam period, I don't have any designated office hours, but I'm pretty available. Just email me and we can book something and go over anything you have issues with. Okay, so I will say a couple of things about the exam now, though. The exam is scheduled now for Tuesday, so it's swapped places with Mary France's exam, so we're second now, and it's a 2-hour exam, and it's 100 marks. So if you remember your tests were basically 20 marks. So this is slightly longer than 4 tests. And in terms of the time, 2 hours is, most people are good with 2 hours for that. I'm going to have, I can't remember what the exact breakdown is, but probably about a third of the test will be multiple choice, true, false. And then most of the other things, you've seen these kind of questions before, fill in the blank, short answer, and all the major calculations we've gone through before. So I think we have room S205 booked, which is basically right across the hallway from the room I'm in now. And it's a pretty decent room, well lit, lots of space, and hopefully things will be nice and quiet in there and no rattling heating vents. That's what I'm hoping anyway. Okay, so let's move on and talk about air quality. This is where we left off last day. I was about to talk about carbon dioxide and kind of just talking about what climate was versus weather. And what this means, because it's something that a lot of people get confused, right? Because they're kind of related concepts, but climate really is the long-term trends, right? So you can look at things like average precipitation or kind of what the typical temperature ranges are in a certain month of the year or something like that. And so when we talk about climate change, we are looking at these long-term, often referring to temperatures, but also other parameters around that are measured by weather. So here's what we want to talk about a little bit today is CO2, but also how do we figure this stuff out? Like what's going on historically? We do have weather stations that have been tracking weather for as early as 1820, apparently, in some places in the world. Obviously, most places in the world did not have weather stations in 1820. And there are some questions around the reliability of instruments. And there are questions around things like, I don't know if anyone's ever heard of the urban warming effect. That means just as, you have these weather stations and typically they were, on the edge of a town or a farm field. And now, as the cities expand, there's more concrete and that makes everything hotter. So all these things are taken into account. But we do have some data going back quite a bit of time. Most of the best data is the past 50 to 60 years. But we can look at other things. Right, so you can see here's a couple of things that are looked at, and I'm going to talk about ice cores in a little bit more detail. But one thing we can look at, for example, is you can look at fossils that are found in certain parts of the world, and so like you can see this example here of a fossilized turtle shell in northern British Columbia, right? So an area that is now too cold for that kind of animal, but historically it looks like maybe it was possible something lived there, right? So there's a lot of things like that. That's how we know that parts of Alberta, used to be ocean, because a lot of the dinosaurs we dig up are actually aquatic type of animals, right? So kind of the same idea. There's a lot of other proxy type records, and I don't know a lot about most of them. I know a little bit about ice cores, which is why I'm going to talk about ice cores. But I keep hearing about these things all the time. You know, I was reading about what are those things called? So in Australia, I don't know if anyone knows what they're called. They're those big boulder things, and they're fossilized, and there are many layers of biofilms that have been fossilized. You know what I'm talking about? My nephew's in Australia, so he's sending pictures all the time. And there's this really cool area. It's near the ocean, and it's all these giant boulders that are basically fossilized biofilms going back thousands of years. So I was reading about these things, and they can drill in them and cut them, and they can learn things about what was happening in different years. And I think it was talking about you know, different years or different thicknesses, and you can look at the isotopes and all these kind of things. And so there's always people discovering new ways to kind of look back in the historical record. You can see some examples there. And like I said, I'm going to talk about ice cores here in a moment. So let's talk about ice cores. I don't necessarily like to use the word mind-blowing all the time, but this is something that really did blow my mind in terms of how much information we've been able to get from these ice cores. So the two places on the planet where we have basically permanent ice, on land anyway, I'm not talking about the Arctic ice sheet, Antarctica and Greenland. And this ice goes down kilometers. So you can see there's a note there on the slide. It says the deepest are about 3 kilometers in depth. And this is representing hundreds of thousands of years, and in some cases a little bit more in Antarctica. And so they have these ways to drill down the ice. There's a little diagram there that's talking about how they drill it out. And they basically, they're not going to pull out a 3 kilometer ice core. I think they pull them out something like 4 meters at a time. And they have ways to send the drill bit down and recover the ice core. They store them and they eventually analyze them. And so you can see there's a photograph of an ice core on the right. It's kind of a little bit blurry, but what you're looking at all these banding patterns. So it turns out that these banding patterns are actually showing the different parts of the year, right? So you got summer layers and winter layers, and things are happening in the different seasons. You know, there's a little bit of meltage or not, depending on whether it's spring or winter. And so you can actually count the layers, kind of like tree rings, or you can actually do conductivity measurements. So just using a conductivity meter, and I'm not sure what's different with the seasons, but they can actually go through and measure the different bands and count the different layers, which is very, very cool. And the other thing that can be done is looking at isotope analysis. So one of the key isotopes is oxygen. So oxygen, of course, is in oxygen, it's in CO2, it's in water, and the key isotope is oxygen 18. So oxygen 16 is the normal isotope of oxygen. Oxygen 18 is a heavy isotope, and you can see the number there, it's about 0.2% of the time. So it's slightly more dense, just slightly, right? And so it turns out that when you have higher temperatures, the oxygen 16, compounds with oxygen 16 actually evaporate a little bit faster. So you can actually use this information to reconstruct and estimate temperatures back through geological time, which I think is just like when I had first learned about this. If you go to this link, by the way, you can read about it. And my mind just went, wow, this is really incredible.
Blaine?
Yes.
Are we speaking of oxygen isotopes? I just have a question that are we allowed to breathe them?
Oh yeah, oxygen 18 isn't radioactive or anything like that. And you know, just the natural air right now, 0.2% of that is oxygen 18. So same thing with carbon. Carbon 13 is also natural. It is radioactive, but again, we're eating it on a daily basis, but the amounts are so small that it's not causing us any health effects. And actually, carbon 13, the radioactivity is such a low level, it's not causing anyone any issues unless you're eating an entire pound of it or something like that. But good question.
What about 16?
Oxygen 16 is the normal isotope that we see, and it's fine as well. Both of these isotopes aren't radioactive. They're just naturally occurring. Yeah.
All right.
Good question though. So we can go back and we can measure temperatures. And the other thing we can do is we can also measure CO2 concentrations, because it turns out that gas is trapped. And of course, CO2 will dissolve in water as well as carbonic acid and carbonates. So we can get a measurement and an estimate of the levels going back. And these really thick Antarctic cores, apparently we can go back 800,000 years. And like I said, my brain is just blown that we can actually do this kind of thing. And you can see there's some values right there. And you can see that CO2 levels and temperatures, they have a very, very strong correlation. And of course, this is something that has been talked about for decades now in terms of greenhouse effects and those kind of things, the CO2 and all that. And you can see I have some numbers on there, and you can see that this was measured in 2017. And so in 2017, carbon dioxide was measured at 412 parts per million. And for the most part, pre-industrial, so we're talking about pre-industrial, we mean industrial revolution. So about before 1800, the average levels, they maxed out at 300 parts per million. So we do have a lot more carbon dioxide in the air. And this year, I'm trying to remember the number. I just read it this morning. Apparently in 2020, we were at the maximum recorded levels ever. And I think it was 421 parts per million, something like that, really close to 420. I have to look that one up. I might have it on one of my other slides. The other interesting thing is that's not the only data we can get from this. There are other things in the air that are put into the air historically. For example, sulfites. And sulfites are correlated with volcanic eruptions. And you can see that they're showing these historical volcanic eruptions. So we have these recorded in the regular historical record, and we can actually see it measured in these ice cores when those eruptions happen, because we're looking at these spikes of these sulfites and other pollutants. Again, the Industrial Revolution, these pollutants have gone up, and actually in recent decades, some of these pollutants have gone down because we have more laws around what you can emit and better technologies to remove some of these pollutants from the atmosphere. So really, really amazing stuff, and the amount of data is really incredible. So I just wanted to say there are other methods. I found this one. I don't know if this is this the textbook that you guys use in Neil's class, The Blue Planet? Yeah, so I wasn't sure if that was your textbook, but it mentions these deep sea sediments as well. And so these deep sea sediments, it's just, they pile up over the years, and I guess people dig them up and can date them using isotopes, and they can also look at the temperatures, and this corresponds to what they're seeing using the other methods. So this is always a good way to, when you're looking back in deep historical data, it's always good when you have the data confirm itself, right? Because if you're using one method, I mean, it's possible your method is entirely flawed. And so I'm kind of just showing this slide to show that, these records are confirmed by this second method at least. So no surprise, we are seeing a mean temperature increase. This is shown by many methods. This is showing the historical measurements in weather stations and whatnot. Some people are deniers, but then again, there are lots of weirdos out there. And part of the debate, of course, particularly if you look at what's going on in the United States, the political debate is around whether this temperature increase is human caused or not. And I don't think most scientists are in denial of that, but you can always find some out there that are talking about that. And like I said, the biggest thing is that correlation between our greenhouse gases and the temperature, very, very strong correlation. And I guess, the thing that I always say to deniers that I meet is that, why are you against cleaning up our air? Right? Let's say it doesn't cause climate change, but don't you think cleaning up our air is a good idea? Right? You look at, for example, the Beijing Olympics. and what they did. And they took, I can't remember how many millions of vehicles off the road, or something like 100 million vehicles. And you can look at all the air quality statistics around there. And I know somebody who used to live in Beijing, and she was saying, you know, certain times of the year, you don't even want to make it outside. I'm pretty sure that with all this pollution, we are having an effect, and that there is good data to support it. So let's talk about the greenhouse effect in a moment here. I just want to talk about what does cause climate change. And there are lots of variables involved. Some of these you call external variables, meaning, you know, basically what's going on in outer space. There are solar cycles around, you know, the intensity of solar radiation. And there is something called, what is this, Milankovitch cycles, which I don't really know lots about. But this has something to do with the tilt of the axis and how there's variations in that. And apparently that's kind of longer term. And apparently that has some explanatory power around glacial periods. These are the kind of things that I consult with Neil on, but haven't had a chance to do so. He knows a whole bunch of those stuff. He knows so much. Neil is so smart. And then there's internal variables. So all the usual suspects, things like volcanoes and whatnot. The one I want to talk about, of course, is the greenhouse effect. But there are a bunch of other things. You can see this example here, change in albedo, that has a lot to do with snow cover and cloud cover. So snow, for example, is white and it reflects radiation. And so if you melt a bunch of ice, for example, let's say we painted all of the glaciers in Greenland black, it would absorb heat, right? And that's what it's talking about. So cloud cover and snow cover, and you can see this kind of thing in some places that as glaciers recede, the meltage happens a lot quicker because there's more ground exposed, which absorbs more radiation and those kind of things. And that's why some years when we have on the other effect, we have you know, a volcano goes off and there's more soot in the air, and so you have a cooler summer. So I remember reading about a number of years ago, I don't know what year it was, sometime in the 1800s, there was a year known as the year of no summer. And I'm like, wow, that's horrifying. What's that all about? So I read a little bit.
Oh yeah, the eruption of Mount Tambora.
That's the one, yes. I couldn't remember the name of the mountain, yeah. And I think, was that in the Philippines? I can't remember where that mountain is. But yeah, it affected great parts of the globe. And a lot of people, of course, had crop failure and all that because, of course, the sun was being reflected off of the extra soot in the air, right? And that's what we talk about when we talk about nuclear winter as well. But there's a whole bunch of other things here. I don't really understand a lot about ocean circulation and continent shifting. But you can imagine they're going to have effects on the weather in terms of, you know, you look at how coastal weather is different from continental weather and all that. And those things can all have an effect. So let's talk a little bit about the greenhouse effect, also called atmospheric filtering. I don't know if this is something you talk about in Neil's class or not, but it's pretty straightforward. It just means that you have these gases in the air that can help reflect radiation back to the earth. And actually a big part of the greenhouse effect is a good thing. Earth would not be very habitable without the greenhouse effect. You can see that number there, that the earth would be about 33 degrees colder than it is today, which means we would not have a summer at all without the greenhouse effect. Of course, the concern is that if we have too much greenhouse effect, so we have excess greenhouse gases in the air, we're going to heat the earth up too much, and that's going to have negative effects on the planet. So I have a little video here I'll play for you that kind of explains it nicely. Just got to make sure I have my sound is shared. And I'll play that for you. It's a pretty short video. I think it's 2 or 3 minutes long. I'll play that for you right now.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable -18 degrees Celsius. And even deadlier, they range from -170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder. Thanks so much to the great
Okay. Anyway, that's the
team over at Kurzgesagt for doing the animation.
How do I get to the next slide? There we go. All right, so that's the greenhouse effect, kind of in a nutshell. And so we talk about these gases as greenhouse gases. So if you ever see GHG, that is what we're talking about. And there are a whole bunch of them. Carbon dioxide is maybe the most important, partly just due to the abundance of it in the atmosphere. And so it is the greatest contribution to the greenhouse effect. You're probably aware carbon dioxide is from respiration, but it's from all sorts of other things, right? Combustion of fuels, so forest fires, human combustion of fossil fuels, and there's CO2 trapped in all sorts of things out there that can get released, and same thing with some of these other greenhouse gases. So I'm mostly going to talk about CO2. So here's another measurement. This one, I was thinking it was from NASA. It's from NOAA, which I can't remember what that stands for, but they're showing the last few years, and you can see right here, since 1950, this goes up to 2020. These are the highest ever measured in the record. And I think I just saw an article recently that said we're estimating this is the highest level we've had of CO2 in 36 million years. I'm not sure how we measure back 36 million years, but yeah, that's a long time, and this is something we're concerned about. And so, like I said, I had just read that this number here, I think, is 421 now. I just didn't have a chance to change it this morning. I was just reading about, I think it was actually in the BBC News, where I'd seen it. I was talking about a recent report. So the question is, climate change, what is this going to do? And that is the real question. There's a lot of this that we understand well, and some of it we understand poorly. The big things that are talked about the most, of course, are temperatures. But this includes a whole bunch of things, right? If you think about all the possible things that can change with temperatures, things like sea ice and sea levels and whatnot. And I also want to touch a little bit on ocean acidification as well. So if you take a look at, like I said, temperatures, there's that correlation, CO2 levels and global temperatures. And so this is going to change, in theory, a lot of things. And so there's these, I really have a hard time keeping track of these political meetings. In fact, I try to ignore reading about them in the news because I'm so uninterested in politics. But with climate change, there was a big key thing that happened in 2015 called the Paris Agreement, where I'm not sure how many nations, quite a few, got together and had agreed that they wanted to limit the rise to about 1.5 degrees Celsius. And I think, what does it say on there, what year? I think they were thinking the year 2100. But at the moment, it's going to be that high by 2040, is where the current trend is. This was something that has been talked about, particularly again south of the border. I think the Republicans under Trump decided they were going to pull out of it. That was like one of the first things they had done, saying it wasn't fair to the US and blah, 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 a bunch of political stuff that my eyes just glossed over on and decided not to pay attention to. But this is something that is talked about a lot in terms of, these goals and whether we can meet them or not, and what needs to be done and how fast. And this is part of the debate, right? Do we need to go to zero carbon tomorrow? Well, that's obviously not possible. But what is a reasonable timeline is a good question, right? One thing that we do know is that in the past 50 years-ish, precipitation has changed in Canada. And you can see that the arrows that are pointing up, the light green arrows, is showing areas where there's we've noticed increases amount of precipitation, and the arrows that are down are decreased areas. So crazy thing is that this includes Alberta and some of the prairie provinces that have a decrease in precipitation. And this is where we have a lot of Canada's agriculture. So I don't know whether the current predictions are matching this as well, but there is data to show that this is the case. It's not huge, at least in the prairie areas. It seems to be more significant in the coastal regions. But this is something, that I guess we have to look forward to. I've seen all sorts of predictions around this around the world, and my understanding is that the more extreme changes are going to be at the equatorial regions, because of course it's going to be hotter there, and hotter usually means more evaporation and drier conditions. And so possible things like expansions of deserts and whatnot. So another thing that's talked about a lot is the Arctic sea ice. There's a bunch of numbers there and whatnot, but what I want to show you actually is an animation. So hopefully this animation is running on your end, but this is showing measurements of the Arctic sea ice. And the animation will repeat. It starts at 1980, and you can see that as it's measured over the years, we are seeing a thinning and a decrease in the amount of permanent sea ice is what we're looking at as well. And there's lots of numbers around this, and it's something that I haven't been following too much, but it's something that does end up in the news kind of annually nowadays as scientists are understanding the magnitude of what's going on there. So something that I have been paying a bit more attention to, though, is this whole, all these announcements about sea level rise. And particularly, there's been lots of stuff in the news in the last few years about Greenland. So I've never been to Greenland, but I have several family members who have been to Greenland. So when I hear about it in the news, it's like this amazing exotic location that I'd love to go to someday. So every time we hear about Greenland, it's just amazing. It's a really large landmass, and it has a really huge amount of ice, and it's not as polar as Antarctica, so it's a little bit more susceptible to climate change. So you can see there's some numbers here about sea level rise in general, and let me just take a look on the next slide for a second here. This wasn't the map that I thought it was. I had another graph kind of showing what the projections are, but you can see some notes here that by the year 2100, it could raise as much as 13,000 millimeters. So that's like a meter, right? I don't live at a coastal area, but I can only imagine how many places will be affected by raising water by a meter. I've seen it in some places, a favorite place I used to go as a child. I used to have an amazing beach, and I have no idea whether this particular lake has anything to do with climate change or for other causes, but most of the beach is gone, and the water is not really that much higher. You know, maybe a whole like 15 centimeters, right? So it was a nice shallow beach, and most of it's gone now, and it washes away and erodes a lot quicker too, right? So Greenland, like I said, I keep hearing about Greenland in the news, and I keep reading about Greenland, and apparently has enough ice. If it was all melted, the sea levels would be raised by 7 meters. I'm just like, holy cow, that's an amazing amount of ice. And I saw this this video a couple of years ago. I think it was at one of those film festivals about these guys who went kayaking there, and they went kayaking or canoeing or whatever they went, and it was literally a brand new river because of all the meltage. And so for them, it was exciting to see something new, but also shocking to see, you know, that this had previously been a glacier there, and now it's gone, and there's an actual river there. So kind of crazy stuff. Here's some numbers. Past 26 years, Greenland ice melting has contributed to 11 millimeters in sea level rise. And I don't know if it was 2020 or 2019. There was a 1 month period where the Greenland ice contributed to 1 millimeter in 1 month. So it's been more than a millimeter of increase per year just due to ice melting in Greenland. And if you Google it, there's all sorts of these studies showing, you know, because every year there is areas that do build up in ice and areas that decrease in ice. And I was going to try to show you some of this data, and you can see these maps. And the maps basically, you see Greenland, you see blue areas where it's an increase in ice packing, and the red areas where there's a decrease in ice packing. And the red areas are much bigger than the green areas. And so this is one of these things that people are watching. They're very concerned that there could be an acceleration in the ice meltage in Greenland, and obviously Antarctica as well. I'm just not paying attention to Antarctica as much as Greenland from my personal interest. But you can see there's the predictions in the next 150 years or so, and there are different predictions. And this is just due to Greenland. Like I said, if you look at all the other ice, the prediction is about 1 meter by the end of the century, which is like, this is just crazy stuff, right? You know, I don't know how long we're all going to live and how much we're all going to see regarding this, but you know, we probably are going to see some significant changes in our own lifetimes. So what else can climate change do, or at least carbon dioxide levels? One of the big things that we talk about a lot is acidification of the ocean. So you probably remember our formula with carbon dioxide. We were talking about carbon dioxide a while ago. Remember, we've got CO2 and it combines with water. And what do we make?
Carbonic acid.
That's right. So we have carbonic acid, and that, of course, is an acid. And a lot of organisms out there, shellfish and corals and things like that, have various minerals as a part of their shells and organs. So a lot of those minerals are things like calcium carbonate. There's other carbonate substances, and all those are sensitive to acids. And I was trying to find some numbers for you. Again, I kind of just ran out of time this semester to kind of get this together. But there are measured decreases in the acidity of the ocean. And there's a lot of data to show that these coral reefs, some of them are failing because of the acidification there, and some shellfish are quite sensitive to it. Of course, the big issue is that these coral reefs are massive habitats to all sorts of other organisms that are living there and finding food. And there's lots of speculation about, you know, what exactly this is going to, what the result is going to be, but it's probably not going to be good. There's kind of a little explainer there. You can see the ocean acidification, and this is just from online Encyclopedia Britannica, but I kind of like the diagram. It's relatively simple. So this is saying in the late 1800s, the sea pH is about 8.3, I think was what they're saying. And I think currently at the moment it's close to 8. I can't remember where I read that, and they're projecting that it'll be about 7.8 by 2100. And you can see they're showing, you know, how this is affecting the shellfish. They're going to be fewer and smaller, and that's going to affect the whole food web, of course. So there's lots about this stuff on the internet as well, if it's something you're interested in. And certainly, again, I have my nephew in Australia, and I know he's done some, he's gone and seen the Great Barrier Reef a few times, and that's something that's in the news a lot in terms of big sections of it collapsing, and presumably due to this issue. So I had mentioned there are other greenhouse gases. I don't want to get into all of these gases. We just don't have time to do it any justice. But you know, it's worth mentioning there are other greenhouse gases. And carbon dioxide, in terms of its effect, is actually pretty minimal. The biggest thing with carbon dioxide is actual quantity. Most of these other gases are found in very small quantities. You can see where they're coming from. So methane, for example, is another big greenhouse gas. And it's 25 times more powerful as a greenhouse gas than CO2. We get methane from, well, cow burps and cow farts. It's produced by microorganisms in part of the decomposition process. So it's actually produced by archaeal organisms. And so, you know, anywhere where there's decomposition. So if you've ever been out in a swampy area and bubbles come up, it's usually methane. You can try lighting them with a lighter and see, and you'll know if it's methane. And lots of places, right? And so agriculture is a big human source of methane, and any decomposition you have. And I think I mentioned that, you know, any places that produce methane, they're supposed to burn it off because, you know, you might as well produce CO2 as a less bad greenhouse gas than methane, right? And some places are taking advantage of it as a fuel, like I mentioned with the wastewater treatment in Edmonton. They're actually using it to produce electricity and heat. There's all sorts of other things. You can see nitrous oxide is another big one here. That one is associated with automobiles and other industrial processes. Again, I'm not sure exactly how common it is in terms of, but you can see it's 298 more powerful than greenhouse gas. But these fluorocarbons, hydrofluorocarbons, and these are found in refrigerants. So, you know, this is one of these reasons why, you know, when you have a fridge to dispose of, the proper procedure is they have somebody drain it of the coolant and make sure that they dispose of it properly before, you know, the fridge itself is just thrown in the landfill or wherever it goes. I don't actually know what they do with old fridges, but probably the landfill. Everything seems to go to the landfill eventually. Kind of makes you sad. So anyway, I didn't want to talk about these too much more. Like I said, just covering each of them is going to take too much time. I was hoping to find out. I was really curious the whole methane question, right? Because we have a lot of cows in Alberta, but I didn't get a chance to figure out how many cows we have in Alberta and what kind of effect that has. So I'm really curious about that because every time
Blaine,
I see cows everywhere. Yes, question.
It's just a general knowledge, but in water and liquids, parts per million is equal to milligrams per liter, right?
Yeah, that's correct. Yeah.
What about for gases? Is it also milligrams per liter, or is it something else?
That's my understanding. Yeah, it's milligrams per liter. Yeah.
For everything?
But, I'm pretty sure, but you know what? I will double check that and get back to you on that. That's a very good question.
Okay, I just want to make sure.
Yeah, I'll check on that and see what I can find out. But you're right. Liquids could be different from gases. You're sure, for sure.
Okay.
Yeah. Okay. So you may have seen. I just wanted to show you and talk about this here just for a second. This CO2e. That means carbon dioxide equivalent, or the global warming potential, and just show you what that means. And I think I kind of had mentioned that just a minute ago. But that's really just, you know, how that particular gas is compared to CO2 for being effective in capturing the sun's rays, right? And they've, I don't know who decided on this exact principle, but they've decided over a given period is 100 years. So if you take a look at all these gases, some of them do break down, like these hydrofluorocarbons, they do break down over time. And so that's a good thing. They do break down, but some of them are, they break down quickly, meaning they're in circulation for months. Some are in circulation for years. I'm not sure about carbon dioxide and methane, but this is part of the measurement. So they had to decide on some bar, and somebody decided 100 years was a good bar, I suppose. And so you can calculate this, and you can see, for example, 1 kilogram of methane is 25 more times effective, and so the CO2 equivalent is 25. So relatively simple concept. So I just want to talk a little bit about trends, greenhouse gas emissions, and a little bit about Canada and Alberta here for a couple of minutes. This is not just CO2, but this is greenhouse gases in general, and this is looking at 1990 to 2014. So there is that upward trend, and of course, this is what we're all concerned about. What's going on and how this is going to affect our climate change. The big one is CO2. The second most important one is methane, and the third most important one is nitrous oxide. And the fluorinated, those are the hydrofluorocarbons, are kind of the other major one. There are other ones that are so small, they're kind of like, I don't know how many decimal places in there without looking at the data, but a lot less significant. So CO2 is the big one, right? And the big contributor from humans, of course, is burning of fossil fuels and other things that we're burning. Mm-hmm.
Would the biggest contributor of nitrous oxide be like equipment?
I don't know. Yeah, Aisha's asking if the biggest contributor of nitrous oxide is diesel equipment, and I'm not sure. Yeah, I know it has something to do. I know there's a lot produced by combustion engines in general. I don't know what the contribution is, diesel versus gasoline versus even other industries, because it is pretty common in a lot of industries, right? I think the difference is it's in larger industries, it's easier to scrub it out, but I'm not 100% sure about that. But good question. So what about Canada? Oh, Canada. So CO2, biggest one here, probably no surprise there. The same order. The percentages are just a little bit different, but same trend, probably no surprises there. So this is showing the trends in greenhouse emissions, and you can see, so we're looking at this one here is CO2, and this one here is, that's all. That's all. This one is CO2, and there's methane, and so on. And all increases since 1990. But here's where it gets a little bit more interesting, is when you start to look at individual contributors, whether you're looking at countries or provinces or industries. And, if you follow international news, probably no surprise here. And by here, I mean China and the US. USA is, the biggest industrialized nation on the planet, doesn't have the largest population on the planet, but in terms of industrialization and economic output, it is the biggest on the planet. And so probably no surprise there that they are consuming and burning more fossil fuels than just about anybody else. They are a rich country, so you would kind of hope that they could get their act together and maybe put this on the decrease. But they have been increasing kind of generally over the years, but not as much as China. So China, has the issue of having, I don't know what it is, 1-point-something billion people, and they are getting richer. In the past 50 years, China has, their economy has picked up, and I don't blame them. People want to have nice lives. They want to have automobiles, those kind of things. But when you're looking at the consumption of more than 1 billion people, this is a major impact. And China is not necessarily the best in terms of their environmental laws. It's a lot easier to pollute in China. And you probably hear all sorts of stories all the time. I was listening to a podcast, and it was talking about a hydrofluorocarbon that had been banned for 50 years. And there was some air quality scientists that were detecting it using these NASA satellites, and it was these rogue factories in China, right? The regulation there, you know, and so they reported to the Chinese government, and they got shut down, kind of thing. But you know, these things happen all the time. We have a large country like that, and the regulation is just so much easier for factories and industries to get away with things over there. Unfortunately, things are changing, but it takes time. And the question is, what kind of impact they're going to have on their environment and the global environment by the time they start cleaning things up. You know, that's always the question about climate change in terms of, you know, when is too late. What kind of timelines do we need to do things on? And some people think it's too late. Other people think we have lots of time. Some people are in the middle. You can see the European Union. Good job. European Union has actually decreased their greenhouse gas emissions, and I don't know how many countries that is, but that is good news. India is on the increase. Same thing. Lots of people. A little bit more economic prosperity, maybe not matching to that of China. But that leads to more consumption of fossil fuels. Canada is right there, and I'm going to just talk about Canada in a moment. Canada has actually decreased our greenhouse gas emissions, which is good news. Not as much as we'd like, but be nice to do a little bit better. So there's Canada, kind of a rocky path. I'm not sure why it's so bumpy. But I'm sure there are all sorts of trends and different things going on in terms of, you know, you've got things like, our economy, gas prices. I know when I first moved to Alberta, the gas prices were just like crazy, and lots of people in Canada were getting rid of their Hummers and SUVs, making smaller vehicles, right? And that certainly probably has an impact on things. But you also have different industries, which is the big thing that's going on here. So one of the big reasons why there has been a decrease has been things like more fuel efficient vehicles, newer technologies. You know, we've got all these greener technologies, more people installing solar panels. I don't know what the impact of that is generally, but the big thing is more fuel efficient technologies has had the biggest impact in Canada and some of the richer countries. So there's Canada there. And globally, you can see there's some numbers. In 2014, we were 19th globally. And in 2016, we were 38th globally. So that's great. I think we can do a little bit better. And finish off this. Who's the problem? Alberta. Again, probably no surprise. It's hugely, this is industry related entirely. We have energy and energy industries here, and we are producing a lot of CO2 as a result of it. We're actually, our output in Alberta has increased. You can see there's the numbers, right? Our greenhouse gas emissions have contributed to 37% of the national. You can see that we've increased 14%. So we do have greener technologies in Alberta, but our output has increased by quite a bit, right? You look at all these developments that have been going on for the last 10 years, and that's where the impact has been. Most of the decreases have been Ontario, and Ontario, of course, is the biggest population in Canada, and so it's, you know, a little bit of a trade-off there. We just see where we are with time. So a couple other things. Look, I've got a couple other slides I'll show you about greenhouse gas emissions. You can see this is showing the different sectors that are the biggest greenhouse gas emitters. And these ones here with stars, these are different aspects of the energy sector. And so overall, that's like 80-something%, they're 81.2%. So probably no surprises there. Unfortunately, that is the nature of the beast. And until people are going to stop heating their homes and driving automobiles, people are still going to be in business here. I know everyone likes to vilify the oil companies, but when there's a demand for something, somebody has to supply it, right? That's part of how economics works. So this is showing, what was this all about? This is showing a 3.9 decrease over all the sectors, and you know, just the different areas. And so you can see it kind of adds up. This wasn't the slide I thought I was going to show. I wanted to show you this one here. This is information from Suncor, and you can see that you know, we had an increase here, so there's a little bit of development there. And this is absolute greenhouse emissions. So this is kind of a little bit better measurement around efficiency. And Suncor has, for the most part, leveled off in terms of their absolute. And I think my understanding for reading this report is that the greener technologies are assuming this will actually start to decrease at some time. Of course, the huge question is the output, right? You know, if you get more efficient, but you're producing, you know, twice as much, twice as much bitumen, you're mining twice as much, you're still going to increase the amount of greenhouse gases over the years. Anyway, that's kind of what I wanted to talk about today. Looks like it's time to finish anyway. So we'll meet back here next day. Like I said, I'm going to talk about the final exam a bit and finish off this topic on air quality.